All right, ladies and gentlemen, let's do 4.5. 4.5 is just going to continue section 4.4, and we're going to learn a few more tests for convergence, and we're going to kind of round out all that I can kind of teach you about all of these, convergence and intervals of convergence and whatever. This is going to be another sort of doozy of a section. If we were actually in class together, we wouldn't do this in one sitting. So if you want to break this up into two different sessions and kind of watch part of the video now and part of it later, whatever you want to do. But let's get after it with 4.5. The tests Part 2. And this title will sort of become clear to you. This whole talk about endpoints, that's going to not become clear until basically the end-ish of this lesson. But overall, it's like all of the tests Part 2. So we've been sort of accumulating this list of tests, all these different tests that sometimes apply, sometimes don't apply. You got to find the correct test, right? We're going to just keep building on that list. Fun! Okay, what does this start off as? We got some explorations. I'll leave it on the screen here for a second or two, but so you can try it if you want to, but I'm going to skip it. And I'll leave just so you have the ability to pause and look at this if you want to do your own exploration, and then I'll leave it on this screen for a couple seconds in case you want to pause and try this later. It's up to you. Okay, here we go. The next test is the integral test. So just to kind of recap, okay, just so we can get kind of a grip on our perspective, right, in our big picture. We've already talked about, I don't know how many tests, right? The nth term test, the geometric test, p-series, direct comparison, ratio test. I think I just covered them all that we talked about in 4.4. But what I'm trying to say right now in review is some of those tests are really, really straightforward. And it's really easy to know when those tests apply and if they're going to work out, you know what I mean? And then there's a test like the direct comparison that is a little bit, not fishy. It's really tough to figure out like when to use it, what other series to compare your series to. I mean, there's a lot of uncertainty with that one, and you just need a little bit of experience and I don't know. So, that test might not be one of the first ones you try. It might be towards the bottom of your list. Who knows? So this integral test, how crazy is this one going to be? Well, I mean, not that crazy as far as when it works, because let your, series, whatever, right, be a sequence of positive terms. All the terms that you're adding up or whatever, they all got to be positive. And suppose that if your series was basically a function, okay, like, which wouldn't be that, just kind of like think of it as a function, right, like an equation, okay, and it'd be a continuous function, it would be positive, and it would always be decreasing after a certain positive x value. So as long as after a certain, it doesn't even matter, after a certain positive x value, if your function was always positive and always decreasing, this test applies. And I'm going to give you a very clear idea of what that basically, how you can kind of check that when we do the example. So stay tuned a couple seconds. Then our series and the integral okay, from wherever, doesn't even matter, to infinity, either both converge or they both diverge. So if you have a series that kind of fits all these criteria, the series is going to do whatever the improper integral does. That's actually pretty straightforward. All right, so, pause if you got to write this down. As always, I'm moving on. And here's the example. Right now, I don't want to, insult your intelligence here, okay? If you were to look at this series in a vacuum, 1 over n times the square root of n, well, you know what? This is just, couldn't you could actually, this is weird. You could actually simplify that together. N to the first times n to the 1/2. Anyway, whatever. That's not important right now. What is kind of important is that you could look at this and, again, if this was like in a vacuum, or if this was given to you on a test, on an exam, and you had like your whole long list of all these different tests you could try, I'm thinking P series. Okay, like I think the P series applies here. Okay, to be honest. But anyway, we're going to apply the integral test. And here's why it applies, okay? To check to see if it applies, just graph it. Okay, like literally graph, y equals 1 over x times the square root of x. Like kind of change this into like equation form and just graph it. And just look at the graph. It's very easy to tell via a graph that after a certain positive x value, I mean, let's just say 1, because it hardly matters most of the time. So let's say after this random positive x value, this graph is always decreasing, and yet it's going to stay positive forever. So basically, the integral test applies to graphs that look like this, or to series where if you graph the equation, it would look like this. This would also work out something like, I'm going completely like random and saying like you could also have a graph like this. And it's a horrible picture, but you know what I mean. Like it doesn't have to go down the whole time. It could go like up like this and then down and kind of curl down, and as long as it was decreasing and staying positive after a certain x value, then the integral test applies. So try to remember that you can use that graph to your advantage. Anyway, so this is going to apply to the integral test, and so all we're going to do is now we're going to like actually integrate the improper integral, and whatever the integral does, so will the series. So here we go. Well, I already kind of covered that. Already covered it. And now we actually take the limit. Okay, and again, it's from technically to integrate, we're going to go from 1 to b and take the limit. You know what I mean? So we're integrating and we're using a limit to do it because it's an improper integral. Remember this from last unit? And so, yeah, that's what that actually is. I haven't integrated yet. I just rewrote this, a little bit simpler. So that's integrated now. So you bump up the power and then divide, right? So that's been integrated now. And again, I'm going a little fast. Sorry. So you can pause as needed, but we've already learned last unit how to do improper integrals. So we do this, right? And then if we actually let b now go to infinity, b to the negative 1/2, this should be approaching 0, right? Because it'd be like 1 over b to the 1/2. And then this is just going to be 2, so hey. So I don't know why I didn't write the final answer, because the final answer is that it converges. This series converges because the integral did. See how it converged to 2? That means the series also converges. Okay, so that's the integral test. It's pretty easy to figure out when it applies and how to run it and figure out convergence or divergence. Hey, p-series, we already did this. I'll move the box in though just in case. But we already did this last unit, or at least we should have. Harmonic series, yeah, once again, when p equals exactly 1 and your series is like just 1 over n, it's weird how that series actually doesn't converge. Like 1 over 1 plus 1 over 2 plus 1 over 3 plus 1 over 4, plus 1/5 plus 1/6 plus 1/7 plus 1/8 plus 1/9 plus, forever. And it actually diverges really slowly. Anyway, let's move on. The next one is the limit comparison test. Emphasis on the word. Let's see what color I have. Emphasis on the word comparison. It's another comparison test. So just like the direct comparison test, you have to come up with like I was gonna say totally different. It's probably not totally different. Just like a different series, like probably a very similar series actually, not totally different. But you got to come up with like another series to compare with your series. But let's see how this one differs from direct comparison. Suppose that your series. Well, let's wait a second here. Single zero p converges, then yeah. So once again, as usual, our series is going to be this, a sub n series. So suppose that your series and some other series you're going to compare it to they're both positive, after a certain point, it looks like for all n is, so as long as after some certain positive n value, as long as both of these series, yours and the one you're comparing it to, are positive, then here's what's going to be true. If you take what happened here? This is supposed to be n probably. Not sure what happened there, but yeah, good as new. Anyway, so if this is satisfied, you can take this limit of your series divided by the comparison series, and you get your answer of C. Like you get your limit, okay? And I know all this seems really weird at first, but you get this limit of C. Now, if C equals 0, then it's good if your comparison series converges. So this is one of the good combinations, okay? You end up with a limit of 0, and as long as your comparison series converges, then your series also converges. You can conclude that your series converges if this is the case. Now, you could also have this as the case and be in business. If you end up with a limit of infinity and your comparison series diverges, if you have that magical combination and the stars align that way, you could say that your series also diverges, and you can make that conclusion. All right? Now, and this is, I know it gets even more convoluted, but this is actually good news here, number 3. If you get any other answer between 0 and infinity, if you get a limit of 2 or 1/3 or whatever, right? If you get any other answer, then guess what? Whatever your comparison series does, yours does. If you end up with this kind of limit, anywhere in between 0 and infinity, and your series is going to do whatever the comparison series does. That's actually pretty good news, you know what I mean? So, so you can see why it's called the limit comparison test. You're taking a limit, and the comparison is done just as like a ratio, so it also has like a ratio test element to it. Well, I guess I don't want to make this too complicated, but there is a ratio there, right? So here we go. First of all, let's see here. Does this converge or diverge? And once again, I know this is going to be one of the crazier tests. What you might want to do first is the nth term test, but I'm looking at this and guess what? The nth term test is going to be inconclusive. You could see if it's geometric. It doesn't look geometric to me. It doesn't look like a p-series. You know what I mean? You could try the integral test, blah, 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 but, direct comparison, but, once you kind of exhaust all those options, then, maybe you get to like a direct comparison or maybe like a limit comparison. So as long as these terms are positive, all these boxes. So, similarly to the direct comparison test, you're going to kind of like chop away at this and find like, you know what, we could like chop off the plus 1 and all this down here we could just think, just kind of chop off some of the other terms, like if you were to, anyway, it's n squared. Or, this technically simplifies to 2 over n. So we can sort of compare this, okay, to this. And I'm thinking this is a p-series that diverges. We're not even going to go with 2 over 1. We're going to go with 1 over n. I bet each one would work, but so we're going to go with 1 over n, and like I was just saying, our comparison series, which again is similar to that kind of, it's a p-series which diverges. Okay, because remember it's actually that infamous harmonic p-series, but it does diverge, and so now we do this limit. So it's going to be this series, because we call this a sub n, we call this b sub n, duh, and we're going to divide them. Now, once again, back to 8th grade or 7th grade, dividing by a fraction means you multiply by the reciprocal. Okay? And this is actually going to be fairly easy, I think, finding this limit. Actually multiplying this together, you would get like 2n squared. So basically you have like 2n squared over n squared. Those are what really matters when you only take like the significant like terms or whatever. So you end up getting 2. Now, what does that mean? We got a limit of 2. That's this case. So our limit was 2, which means whatever this series does, so does ours. That worked out pretty good. See, once again, the tough part is, what do you compare it to? Just figuring out that, this is the test that's going to work out for you, one of the comparison tests. I'm pretty curious to see if the direct comparison test would have worked. Let's see here. Would this be bigger than that? I don't know. You know what? I'm not going to waste our time right now. Ooh, another one. Okay, okay. So, all right, gang. What do you think if we're going to do the limit comparison test here? We could try other tests if you want to, but limit comparison, what do you think we would compare this to? What do you think? 1 over 2 to the n minus 1. What could we just compare this to? Goodness. 1 over 2 to the n. What do you think? Yeah, see how, I mean, you kind of see one of the typical strategies, to finding a comparison, a series to compare it to. And all right, so what does this do? What does this do? Does this converge? Does this diverge? And how do you know? What do you think? 1 over 2 to the n. Does it converge? Does it diverge? And how do you know? What test could you apply? What test do you think applies here? I'm thinking geometric. Yeah. And since your R value is 1/2, right? Remember how the geometric test works? This would have our R value, our common ratio, as 1/2, which makes it converge. It's a magic common ratio value. All right, so now that we know that our comparison series converges, we can go ahead and do the limit. All right? So our series divided by that one. Okay? And how would we figure this out? Would we do that special algebra trick where, because you can't cancel, right? I mean, are we going to like smush these together at first? Is that, oh goodness, yep. Yeah, are we going to do this algebra trick? Multiply top and bottom by something? What do you think? Remember from last section? All right, let's see what this does. So multiplying this times that, that's just going to be a 1, right? Okay. And so multiplying this through, distributing through the bottom, we get to this. And now, letting n actually approach infinity, you can kind of like wrap your brain around that and going like, well, letting n go to infinity, this whole fraction would just approach 0, and so it would equal 1, right? Letting n approach infinity back here is just like infinity over infinity, you know what I mean? And I'm not sure if L'Hopital's rule could be applied here, but this works. L'Hopital's rule might have also worked, but we go from infinity over infinity to basically this, and we get 1. And guess what? So if you get a limit like that, that means our series is going to do whatever that series does. So our series also converges, right? So once again, right, like I know, and I'm taking a step back here again, but I know it can be overwhelming, all of these different tests, you know what I mean? But I mean, with a little bit of practice and a little bit of time, you can start to get comfortable with all the different tests, with all of their different, criteria and restrictions, and all like the rules about when a test will apply and stuff like that, and how it works or how it works. And hey, you have all these notes as a reference, doing your homework and maybe even doing a test or something, like an exam, I mean. Another example for, geez, well, maybe by now you're getting the hang of this. So once again, I mean, you could try nth term, geometric, p-series, I mean, whatever, direct comparison, ratio test, but maybe you're starting to learn, just almost like, not immediately, but after maybe look at it for a few seconds, and you look and you go like, yeah, this actually does look like something that is going to have me doing one of the comparison tests. This doesn't look like something I would do the ratio test on. It doesn't look like geometric, or you know what I'm saying. You'll start to get a hang of it. So looking at this, what do you think we're going to compare it to for our limit comparison test? If this is the series, what do you think? See, like maybe once again, maybe chop away the plus 2 and you chop away the minus 2n, and you're left with that. Which, if you have that, you might as well reduce it and clean it up, and just get that 3 out of there. So 1 over n squared. So we're going to compare it to 1 over n squared. Now, so again, we have to know what this series does. Does this series converge or diverge? How do you know? It converges by what test? By what test? P-series. It's classic P-series. All right. So now it's time, now that we have our comparison series, now it's time to do the limit part of things. So a sub n divided by b sub n, multiplied by the reciprocal. And what's going to happen? We're going to have, like, if we actually multiplied, we'd have like 3n cubed as the important thing over n cubed. Oh, I know what's going to happen here. Oh, geez, okay. All right, yeah, baby steps, writing out my work, okay. What's this limit going to equal? Huh? What's it going to equal, huh? 3. That's a great result because, once again, geez, every single example has been this. But don't forget about this also, people, right? Again, if you happen to get 0 as your limit, as long as your comparison series converges, you can come up with a conclusion. As well as this other situation, it seems like we're always getting this, so, but that's a good thing. This result means that our series is also going to converge. Cool. Another one. Holy schmoly. Well, here we go, man. What are we going to compare this to? Huh? I'm going to go ahead and make a bold claim that this is going to be like kind of a specialty example. So recall, what does this equal, people? Sine of x over x as we approach 0, what's it equal? 1. Okay, so our comparison series is going to be 1 over n, which is the harmonic p-series. Okay, 1 over n. And so when you try your limit, so kind of remember this. I mean, this is a very, to me, this is like a very specific example. The sine of 1 over n, and then using 1 over n as your comparison series. Let's see if it works out. Bold strategy, Cotton. Let's see if it pays off. So far our limit has, let's see, if you let n approach infinity, this approaches 0, and so the whole sine approaches 0, and okay. Now, do you guys remember what we do when we end up with 0 times infinity? We have to rewrite it. And I'm going to use this very cheap way to rewrite it, okay? Instead of multiplying by n, divide by 1 over n. It's almost too easy. And that's going to result in now 0 over 0. Hey, what can we do with 0 over 0? Remember this from Unit 3? We can do L'Hopital's rule and get where? What's the derivative of the sine of 1 over n? Cosine of 1 over n. Don't forget the chain rule. Also the derivative of the bottom. There's canceling. So if we let n approach infinity now, especially after these cancel out, Cosine is 1. Yeah. Hey, once again. Gosh, we can just, this series does whatever. Yeah, so our series also diverges the same as our comparison series. Holy mother, are we finally going to be done with the... Thank the goodness. Alright. So, jeez. That limit comparison test was something else. The next test is the alternating series test. Okay? Alternating series test. I'm not even going to pretend to know how I pronounce that, but Leibniz, the alternating series test. Okay? So, the series, okay, which has to alternate, here's some good news. The alternating series test, it's probably one of the tests you want to do if your series is alternating. If it's like alternating sign, positive, negative, positive, negative, positive, negative, right? And so if your series includes something like this, with like the -1 to the n power or n plus 1 power, you might want to think about trying the alternating series test. Okay. So an alternating series converges if all 3 of the following conditions are satisfied. All of these terms are positive, other than the alternating part, right? If all of these are positive, so basically if it alternates. And if it's getting smaller, so if like the next term, if every following term is like equal to or smaller than the term right before it, and if these terms are approaching 0, right? All these, again, this u sub n part is almost like separate from this part that makes it alternate. So that makes sense. I mean, right? Like if these terms are getting smaller and smaller and smaller and smaller, basically approaching 0, then yeah, I would think this is going to converge to something. So this one is not all that difficult to kind of go like, yeah, that makes sense. That's going to converge if it satisfies all of these situations or all these conditions. So here we go. This next part I'm going to kind of brush over pretty fast. I'm not going to emphasize it that much. This truncation error thing, if it pops up on something, let me know. But I will at least show you these notes, and you can, to a certain extent, these notes can like speak for themselves. Like this reading, okay, and this little piece of business right here. So if you want to look at that later, pause and look at it. Be my guest. Alright, here's this next thing. Big old star. Not bad. When a series converges, but doesn't converge absolutely, it is said to converge conditionally. So write that down. Okay, and perhaps you recall from last lesson that if you can like throw an absolute value on your series, you know what I mean? And if you put an absolute value in there and your series converges, then you're allowed to say that it converges absolutely. So converging absolutely means it converges when you put absolute value into the series. Okay? And again, like there was a little bit more to that story. If your series converges absolutely, then it converges, period. It converges, you know, without the absolute value or with the absolute value. Like it just converges, period. Okay? But this, okay, is sort of like, I don't know, the other side of that coin. It's like if your series only converges if you leave it alone, it converges if you leave it alone, but if you throw absolute value in there, it actually makes it now not converge, right? If it only converges if you basically leave it alone, which seems like, yeah, leave it alone, then you can say it converges conditionally. Okay. How to test the power series for, well, I'm not going to go through that. I mean, we're gonna live it right now, okay? Gang, if you haven't broken this lesson up yet, like if your plan was to do this in 2 sittings, I wish I could, but it's too late now. But this might be a pretty good place to stop, or just power through like I'm going to do, okay? So here we go. Because the objective from here on out kind of changes. Because look at the directions. For what values of x do the following series converge? For what, not does it converge, period, or does it diverge, period. Now, for what values of x do the following series converge? Now look, we've done this before, okay? Like take comfort in that fact. We were doing this last section, okay? Now I'll pretty much let the cat out of the bag, the difference here now is that we are going to check the endpoints. Whoa, slow down, Mr. Falk. What are you talking about? Well, even like, okay, last section, we were using the ratio test, right? And, you might even be able to use like the geometric series test, but it's going to usually be the ratio test to come up with like an interval of convergence, a radius of convergence. You had an interval, right? And let's say your interval of convergence was like -1 to 1. The classic one, right? -1 to 1. Now, I'm here to tell you that we actually need to now check the endpoints, like the endpoints of that interval. And that's what we're going to do now. All right? So we're going to do the ratio test. Okay? We're going to do the ratio test to figure out, what the interval of convergence is. The ratio test is great for that. Okay, just is. Now, the ratio test, listen to this. It's a it should be a reminder, but the ratio test only applies when all of the terms are positive. So that's why we have to throw this absolute value in there. Okay? That's just so we're actually allowed to do the ratio test, because it's always going to be positive. So remember the ratio test, a sub n plus 1 divided by just a sub n. So we were doing this last lesson, and hopefully there's canceling. All right, this and this, they cancel to be left with just x squared. Okay, and we don't need the absolute value anymore, I guess. And then you're left with this. So now, when n approaches infinity, this limit right here, this will approach 1. And so it looks like we're going to be getting x squared. Now, remembering how the ratio test works, right? The ratio test says that it converges when this limit is less than 1. Remember that about the ratio test? This right here is how the ratio test works. This is when it will converge, when it's less than 1, this limit. And so now we just kind of solve this. You know what I mean? Like we could take the square root of both sides and get plus or minus 1, and when you get to here, okay? And so this, on this interval, you can say is where this series converges absolutely. We threw absolute value in there, and it converged on this interval. So this is where it converges absolutely, okay? This isn't different at all, really, from what we were doing last lesson with the ratio test, okay? But now we're going to check the endpoints. So we're going to check it at x equals -1 and at x equals 1. So check this out. If we leave this alone, no absolute value, right? No, we already did that. We threw absolute value in there so we could do the ratio test, and this is what we got so far for our interval. But when we check the endpoints exactly, we're going to go with like the untainted series, which, by the way, is alternating without all the absolute value. This will be an alternating series. Maybe we're going to use the alternating series test. But, so anyway, let's get down to it. If you literally plug in -1 for x, okay, or positive, I think here it doesn't really matter. Like if you plug in -1 versus plugging in 1 in for x, I think you're going to end up with like the same result, okay? You get what? Like 1 to something, which is going to be +1. Even like -1 to 2 times something, you're going to get like a +1 all over 2n. So, okay. So what does this series do? Does it converge? Does it diverge? Well, we're going to do the alternating series test, okay? And it turns out that this passes the alternating series test because the u sub n part is the 1 over 2n. That's horrible. No way am I going to... Oops, what the heck? Hitting the wrong buttons. What did I just do? Anyway, sorry. Keep hitting the wrong button. So this would be like the u sub n part in the alternating series test. And as long as this just keeps getting smaller and smaller and smaller and approaches 0, then it converges. So this converges by alternating series test. Okay, so listen to this. You could say that your overall interval of convergence is this: -1 less than or equal to x, which is less than or equal to 1. This would be like your overall interval of convergence. You know what I mean? Because remember, converging absolutely, it means it converges, period. But sometimes you could be asked to like split up your answer and say, identify where it converges absolutely and where it converges conditionally. So this is where it converges absolutely, and these two values is where it converges conditionally, because it converged here and here when we left the series alone and didn't throw any absolute value in there. 2 more examples, 3 more examples. 3 more examples. Okay, let's do it. I can do this. Alright. So, ratio test. We're going to throw some absolute value in there. All right. So remember n plus 1, n plus 1. Okay, this is the ratio test. And, ooh, check it out. There's going to be canceling here. And with the factorials, there's also going to be canceling here, won't there? So you end up with 10 absolute value of x. And then when these two things cancel, you're left with just n plus 1. All right. So what's the result of this limit when you let n approach infinity? You get 0. You get 0. We're like, 0. So overall, 0. So what does that mean in the context of like this ratio test? When you get a limit of 0, I mean, it looks like we're always going to be less than 1. So you know what that means? That means this series converges for all x, because your limit was just like 0, which is always less than 1. So this is a thing that can happen. Next example. Oh man. Let's see what happens here. So if we apply the ratio test here, remember it's going to be like a sub n plus 1 divided by just a sub n. And so it's, for a sub n plus 1, instead of n factorial, it's going to be n plus 1 factorial. And then instead of n, it's going to be n plus 1. And then the original is down to there. Okay. So is there any canceling? Yes, there is. Because this is going to cancel, right? We can like subtract these powers. These factorials are going to cancel a little bit. And you're going to get that. Okay? And check this out. When you let n approach infinity, this whole limit, okay, this whole limit is going to equal or approach, right, infinity. So what does that mean with the ratio test? If you get a result of infinity, doesn't that like absolutely fail the ratio test? Like it's just a complete fail? Well, yes, unless you actually had an x value where you were taking this part and multiplying it by 0. What could make this whole thing just flat out equal 0, and then when you take the limit, it's just going to be 0. So what x value would have all this just be 0? -1. So this is a thing that can happen, because this, okay, will approach infinity unless it's 0. And so if x happens to be -1, then this whole thing will actually equal 0. It's be less than 1. It'll actually pass the ratio test. So this is a thing that can happen, okay? One more example. I don't know why they show this stuff. But, all right. Ratio test. Ratio test. I know there's going to be, again, just remember, you got to throw the absolute value in there to even be able to run the ratio test. So there's going to be some canceling here, let me tell you. And then, so what happens when we actually take the limit? This will pretty much just be 1, like 2 over 2, which is 1. And so that is going to be the result of our limit. Now remember, the ratio test, there's convergence when this result is less than 1. Okay? Now, when you have this absolute value thing involved, okay, that means it's going to be less than 1 and greater than -1, and so you're able to write out this. This is just algebra, this absolute value algebra. And so here is your interval so far, but then you just got to like finish solving for x. So you're going to add 3 to middle, right side, left side, and this right here is going to be your interval of convergence, at least for what? Absolute convergence. So this is where it converges absolutely. But remember, starting like with this lesson, we have to check the endpoints. All right. So we're gonna try x equals 2 separately, and then we're going to try x equals 4 and see what happens. So remember, the original series without any absolute value. So we're checking these for conditional convergence. Okay. So if you literally plug in 2 for x, this would say 2 minus 3 to the n power. 2 minus 3 is -1, right? Hey, this is an alternating series, -1 to the n. So by alternating series test, this converges. Okay, so it converges at x equals 2. Let's see if it converges at x equals 4. Again, we are literally plugging in 4 in for x. And so 4 minus 3 is just 1 to the n, which is just 1. That was weird. All right, so when we let x equal 4, this is what we have, right? So what does this series do? Does it converge? Does it diverge? Well, I wonder if by direct comparison, because if you compare this to 1 over n, so you would compare this to 1 over n, okay? 1 over n diverges. Oh man. So the direct comparison test is inconclusive because this is actually smaller term by term than 1 over n. So for the direct comparison test to work, this would have needed to be bigger than 1 over n. Well, guess what? If you were to run the limit comparison test, you'll get a conclusion there. Your conclusion is going to be that it diverges. So check it out. Here, look very carefully. 2 is less than or equal to. Here it's just less than. So it converges at 2. It does not converge at 4. So our overall interval of convergence is this. And if you had to like break it up, you know what I mean? Like as far as like converging absolutely and converging conditionally, this is where it converges absolutely, and it converges conditionally at x equals 2, and only x equals 2. Whew, okay. The last thing I'm going to say is, obviously I'm going to put this on the screen at least for a second because this is just like kind of an overall plan of attack, but this is essentially what I've been saying. We're like, now we have all of these tests. We have the nth term test, the geometric test, p-series, ratio test, direct comparison, limit comparison, alternating series test, integral test. I don't think I said that one. Integral test. So you have all of these tests, and you're just going to try them probably in a certain order, or you're going to learn with experience, like which tests work for like different looking series. So, this is essentially, you have your list, you know which ones you're going to try first, and blah, 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 blah. Whew, I'm spent.